Okay, this is another comparing blocks submerged in water question. It's a little different than some of the other questions because one of the things that this asks you to do is to, as part A, is to list all the forces that are acting on each block, and then it asks you to rank them. So first I'm just going to do the list all the forces on all the blocks, and then we'll do the ranking afterwards. So if we think about, say, okay, so let's start with block one. So we do a free body diagram, right? So we have our block, we have some force acting up, which is the buoyancy force. We have some force acting down, which is gravity, right? And because there's only two forces, these must add up to be equal to each other, right? This minus this must equal to 0. So we have this thing that the mass of block 1 times g is equal to the buoyant force. Well, what's the buoyant force equal to? Well, it's equal to the density of the fluid times the volume of the fluid that's displaced times g, right? What else is this equal to? Well, on this side, this is equal to the density of block 1 times the volume of block 1 times g. Well, what does this lead us to? Well, this leads us to the density of 1 times the volume of 1 is equal to the density of the fluid times the volume of the fluid. Well, we notice that, wait a minute, this block is completely submerged underwater, right? Its volume is the same as the displaced fluid volume, right? V1 is equal to Vf. So it means actually that the density of block 1 must equal to the density of the fluid, and this is neutral buoyancy. Let's look at block 2. Block 2. Well, what do we have with block 2? So let's do our free body diagram, as we usually do. What are my forces? I've got a force acting up, which is the buoyant force, right? I've got a force acting down, which is the force of gravity, m2g. And I also have this other force acting down, which is the tension force from the rope, right? This rope is pulling down with some tension. Well, let's write out the balance of forces for this. So we have the buoyancy force going up. We have m2g going down. And we have the tension going down, and this should be equal to 0, right? So these are all the forces acting on it. I don't know, you can simplify this a bit, right? We could write the buoyancy force as the density of the fluid times the volume of the fluid times g. And we can write this as the density of thing 2 minus the volume of thing 2 times g minus the tension is equal to 0. And once again, right, this block is fully submerged. So Vf is actually equal to V2, right? And we could rewrite this. We could divide by G, and we could write this as something like Vf, or rho f minus rho 2 minus T is divided by some volume, right? We'll make these V, the volume, divided by G is equal to 0. So that's something we could do, but it's an equation. Let's take a look at block 3. Okay. So block 3 is essentially the opposite, right, of the one we just did. The tension force is in the opposite direction. So we still have our buoyancy force going up, right, Fb. We still have our weight going down. But we also have this third thing, this tension force going up. And so our force balance becomes the tension plus FB minus M3G is equal to 0, right? And you know, just like before, we could simplify this. We could write this as the tension plus the density of the fluid times the volume of the fluid displaced times G, and that's equal to the density of 3 times the volume of 3 times G. And once again, these two are equal to each other, right? And so we could write this as T over Vg plus rho F is equal to 3. And those are the forces that are added up onto it. So let's look at block 4 now. So block 4 is this one that we've come up with many times. Right, so the volume of the displaced fluid in this case is now less than the volume of the object, right? And we know that we have this balance of forces that we usually do, right? We have the buoyancy force going up, we have the mass of the block going down, and there's no other force or anything for us to think about. So we just know that M4G is equal to the buoyancy force rho F Vf times G. And if we wanted to write this out in terms of the densities, we could write it as this. And I don't know, we can get an equation. And I don't know, we can get an equation that is, you know, for the density of the block, let's say. So, you know, this is the question we've done many times before, right? Yeah. So I guess right now, the last thing to do is to rank these actual densities. And the ranking of the densities becomes actually pretty easy. So let's look at block 1, block 3, and block 4 first, because I think these are the easiest. Right off the bat, we see that block 4 is floating high above the fluid. All of these blocks have the same volume. So this one's a little deeper, and then this one's actually being held by a rope. And if it wasn't held up by a rope, it would sink. And so just from this, knowing that all of these have the same the same volume, because number 4 is higher, it means that 4 must be the least dense. And then block 1, and then block 3 is the most dense. The funny thing happens when we try to add block 2 into this. Block 2, well, we know that block 2 wants to float because there's a tension force on it, right? So we know that block 2 is lighter, or less dense, I should say, than block 3. However, we can't place it between block 4 and block 1, right? Because we don't know if this block is going to go up. It could rest right here and be equal to block 1, or it could float all the way up here and be even lighter than block 4, right? We just don't know. So we know that it's greater than, or it's less dense than 3, but we don't know how it fits in the whole story with blocks 1 and 4.